The topic for the video is longest repeating substring in linear time. So the problem statement is that we are given a string and we want to find the longest substring that appears at least twice. So the naive approach of solving this problem is to define a function called the longest common extension, or LCE, wherein it calculates the length of the longest common prefix between a certain interval of text. So for example, T1 to N is Mississippi, then T3 to N would omit the first two characters of the string, and the rest of the string is T3 to N. So in this case, it would be Mississippi. So then similarly for T6 to N, it would be Mississippi. And if we were to calculate the longest common extension between these two suffixes, then that would be SSI, as that is the longest common prefix here. So once we compute like all the LCE, the maximum among them would be our answer. The time taken for computing all the LCE would be O of n cube, which is not at all efficient. So using recurrence, we can bring down the time complexity to O of n square, which is not again desired. So before we look at linear time algorithm DC3, let's understand what a suffix array is. So a suffix array is a sorted array of all the suffixes of a string. So in this example, let banana be the string. So here the text ends with a special character $. So this dollar is unique and lexicographically smaller than any other character. So here we list down all the suffixes possible of banana, and I represents the index of the array which begins from 0. So here we take banana $, then we omit the first character, that is B, then we get banana $, then we omit the first character, so on and so forth. So after that we sort the suffixes in the ascending order. So $, comes first, then followed by A, then followed by ANA $, so on and so forth. And this column represents the original index. So when we list down all the original indices, the array that we get is the suffix array. So this array is called suffix array. So DC3 algorithm is a linear time algorithm. That is, it takes O of n time. So this algorithm is used to construct suffix array. So to understand this algorithm better, let's take the example of string Mississippi. So suffix array is like a permutation, and inverse suffix array finds the inverse permutation encoded by the leaf array. So we want to write down the text Mississippi in the text order. So we start with Mississippi, then we omit the first character, take the rest, omit the first character, take the rest, so on and so forth. So here I represents the index starting with 0. Ri represents the lexicographical rank of this. So this is like lexicographically the lowest, then followed by this, then followed by this, so on and so forth. And in the right table we have all the sorted suffixes. So here R tells us the rank of the suffix, and LR tells us the position, the original index position in the text order array. So the first step in DC3 algorithm is to calculate the rank array for suffixes which are not multiple of 3. So for n strings, we are basically calculating the suffix array for 2 by 3 n of the strings. So here we create a new compound triplet character. So for example, in case of let's say Mississippi, so T1 is basically omitting the first character and taking the rest of the string. T2 is omitting the first two characters and taking the rest of the string. So T dash is basically equal to T1 to N. So that comprises of like T1, T4, T7, etc. Then we append it with $3. And then we take T2 to N. So that is T2, T5, T8. And then we append it with $. So we call the suffix sorting recursively on the T dash and map the result to rank 1, 2. So for the string Mississippi, T1 would be omitting the first character and taking the next three, so that is ISS. Then T4 would be omitting the first four characters and taking the rest, that is again ISS. T7 would be omitting the first seven characters and taking the rest, that is IPP. Then T10 would be omitting 0 to 9 and taking from 10, that is I dollar dollar. And then in the end we have dollar dollar dollar. And then for T2 to N, T2 to N, the first T2 that is omitting the first two characters, we would get SSI. Then T5 would be SSI again. Then T8 would be PPI. Then T11 would be dollar dollar dollar. And this is basically our T dash. And then these are our unique occurring triplets. So here, as we can see, ISS is being repeated twice, but we just take the unique values. So we take ISS, IPP, I dollar 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 dollar, SSI and PPI. So then we sort these triples. So here are the sorted triples in the alphabetic ascending order, and here we have the index of the original position in the array. So this was our original T prime or T dash, and this is our T double prime. So T double prime, we find the rank of this by referring this table. So we check the rank for ISS. So for ISS, the rank is 3, so we write down 3 here. Then for IPP, we check the rank in this table, it is 2, we write it down here. So T double prime is the actual string on which we do the recursive call. So using the triples, we then determine the rank for the suffixes. So now here we have like the sorted suffixes, and this basically gives us our first suffix array. The second step is to induce the rank for the remaining suffixes, the suffixes that are the multiples of 3. So here we basically strip off the first character. So in this case, let T, that is the text, be Mississippi, then T0 is taking the first, stripping of the first character, the 0th character, and taking the rest. So that is, the rest is T1 and the first character is M. T3 is stripping of the second character, that is M is 0th, I is first, then this S is the second, so we strip off this character, and the rest of the string is T4. So then we can compare these two suffixes in constant time. So here I've noted down the suffixes which are not multiples of 3. So we strip off the first character and check the rank of the rest of the suffix. So for example, if we take T0, then we strip off the first character, that is M, and whatever remains we check it in this table. So here we find it, so its rank is 4, so then T0 would be equal to M4. Similarly for T3, we take the first character S, find the remaining suffix in this table. So here we have this suffix, so the next thing would be T3 would be equal to S9. So as we can see in this table, we have noted down the version for like all the multiples of 3. We then simply perform radix sort to sort the elements in linear time, as the first component is a character and the second component is a number that is bounded by n. So after sorting, what we get is another suffix array. So the next step is to use the standard merging from merge sort. So here we strip off the first character of both the suffix if they belong to the same table. Then we compare their ranks, else we continue stripping the character and repeating the process. So this would at most take 2 steps. So for example, we strip off the first character of T9, that is P, and the remaining suffix is basically T10, so what we get is PT10. Then for T8, we strip off the first character P, the remaining suffix is T9, so T9 is equal to PT10 and T8 is equal to PT9. So these T9 and T10, they lie in different tables, so we have to repeat this step again. So we strip off the first character of T10, so that is I, and the remaining thing is T11, so we get IT11. For T9, we strip off the first character, that is P, and the remaining thing is T10, so we get PT10. So since I is less than P, therefore T10 is less than T9, and therefore T9 is less than T8. So after performing the merge operation, what we would get is a final suffix array. So for the example of Mississippi, this is the final suffix array. So for the key idea of Kasai algorithm is to compute the LCP values in text order. So for the Mississippi example, the first suffix in the text order is Mississippi dollar. So that is the entire text. So now we check for the corresponding LCP value. So we check this value in the right table. So we find that the string at position phi in this table. So the LCP values are between the adjacent suffix in the sorted order. So the LCP value at phi talks about this suffix and the suffix before this one. So Mississippi dollar in this case. So now we find the longest common prefix between these two suffixes. So we compare character wise to see the longest common prefix. So what we can see here is that here they share nothing. So the LCP entry for Mississippi would be 0. So we make use of previous comparisons to avoid spending more time on the next step. So then we move on to the second one, that is Mississippi. So here we find this in the right table. So we find this element here and we check the element before that as well. So what we can see is that ISSI is the longest common prefix value for this. So we store the value number 4 here. Then we move on to the next. We find it in the right table. We compare it with the element that is previous. We check, we find that SSI is the common prefix here. So we store the number 3 here. Then we move on to the next. We find that SI is the common prefix here. We store the number 2 here. Then here we find just I is the common prefix. We store the number 1. Here we find S is the common prefix. We store the number 1. Here we find nothing is common. We store the number 0. Here we find I is the common prefix. We store the number 1. Here we find P the common prefix. We store the number 1. Here we find nothing to be common. We store the number 0. Here again nothing common. We store the number 0, and the dollar sign just the last character. So as we can see from this, the LCP for the word Mississippi is ISSI, as it is the highest number in the LCP array with length 4. So for step 1, that is computing rank array for non-multiples of 3. So here we deal with 2/3 of the number, that is 2 3n, 2 over 3n. For step 2, that is inducing the rank for the remaining suffixes, that is the suffixes that are multiples of 3. So here we are just dealing with n over 3 numbers. So in step 2, sorting would be possible in O of n time by running 2 iterations of count sort. So first sorting by the second number component and then by the first alphabet component. So on the top level, step 2 and step 3, that is the merging step, would take n time. Then we make a recursive call and we only have 2/3 of the strings to deal with now. So then this step would take 2 3 over n. Then again we have a recursive call, so then we would have 2 over 3 squared n, so on and so forth. So what we get is a geometric series. So the value of this is 3, so we get 3n, and therefore the time complexity would be big O of n. So in case of Kasai's algorithm, when the characters are unequal, we have at most n comparisons. For the equal characters, the value of L is incremented and decremented n times in total. So then that is at most 2n increments. Thus the total time complexity would be n. So thus the overall time complexity to find the longest repeating substring would be O of n.